and that would be secretion. Okay? That is important for, particularly for a lot of organic compounds and potassium and hydrogen ions. So those are the three basic processes. So I bet you in Dr. Monaco's podcast, he probably will talk about the filtration barrier, and he will say that it's kind of like a sieve and it lets stuff through, but only very small stuff. And effectively it's got a, I'll say it's got pores. Things can get through pores in the glomerulus. Effectively, a molecular radius of about 2 nanometers is basically the exclusion threshold. Even though some of the holes are bigger, the molecular radius is 2 nanometers. So I've got a bacterial filter here that's about 200 nanometers. And I'm going to push as hard as I can. She didn't, did she? Now, if I point it over here, I'll get a reaction. Look, I had to push pretty hard. And the holes here are 100 times bigger than the holes in the kidney. So I actually need to generate some work to do that. Where does the work come from? Simple question. It's worth, quickly it's worth, oh, I've lost my, oh, did I put these back here? Where does the work come from? Blood pressure, okay. I was going to say the heart, but it's still worth something. Yeah, you've got to share it with everybody else. Okay. Yeah, you can share those. I think there's probably more than one in those. Okay. And I'll talk a little bit more about energy expenditure later. Oh, just one other thing. Filtration fraction. I'd just like to be sure that we define this. Filtration fraction. So, it's simply this as a fraction of this, okay? So in other words, it's the amount of filtrate as a fraction of the amount of plasma that went through. So that's the filtration fraction. And the reason I want to define this now is later on we'll talk about fractional excretion of sodium and the such like, and I don't want you to get confused with terms. Filtration fraction is just the amount that's filtered as a fraction of what was presented to the kidney. Okay? So, remarkable, the kidney receives about 1/5 of the total cardiac output at rest. That's quite a lot. So does the kidney need that metabolically? Probably not. Probably not. I mean, understand that it's taking blood to, I don't want to use the word cleanse it because it's doing a lot more than just cleansing it, okay? It's taking all that blood because it's processing it. However, what is interesting is that it actually accounts for something like 7 to 10% of oxygen consumption at rest. So, wow. I mean, the kidneys are only this big, guys, and yet they take almost 10% of the total energy expenditure at rest. So, I would put it to you that the kidneys actually do a lot of work. Understand that the heart did a lot of work to filter this stuff in the first place, and basically if you're going to reabsorb 99% of it, you need to do about the same amount of work to reabsorb it. And so it's an energy requiring process. Okay. Golly, you're thinking, who on earth designed such a ridiculous system? You know, you spend all that energy to filter the stuff, and then you spend the same amount of energy to get it back again. Well, I think you guess there's probably some wisdom to it if it happens. And I think the point that I would try to make is that don't forget that the kidney's also a garbage disposal unit. So there's a million toxins out there that it has to get rid of, toxins, bad stuff, whatever. And so, you know, obviously you can't generate a system for getting rid of every toxin. So it's much better. It's like when you clean house, you take everything out, you put it back in you put it in the garage, and then you bring back what you want. And that's what the kidney does. So it's got a myriad of mechanisms to retain the good stuff. There's still quite a few mechanisms, but it doesn't have to have special mechanisms to get rid of the bad stuff. So really not inefficient at all. It does the job. Oh, the only other thing that I would add, do I want to add this? Yeah. I told you that I would try to give you a heads up on exam questions. So the shelf exams often talk about oxygen consumption in the kidney. And so you need to relate oxygen consumption to where most of the work is done. And I don't think I need to take it any further at this stage, but oxygen consumption correlates well with where the work's done. And most of the work is done in the proximal tubule. So I know that you haven't worked with Dr. Monaco's podcast yet, but if I say proximal tubule, is that still a tough concept for any? You've at least done some of that, right? Okay, good. Any questions on the very basics? Okay, let's flip the page. Long and short nephrons. Is there enough light on this board to see? Is that better? Good. So, I'm not going to make a big deal. You see the picture in the handout? So, you got short nephrons and you got long nephrons, okay? And so, so this is cortex and this is medulla. And I don't need you to really take a lot away here. There was a time when I started in science back in the 70s where we were very excited about this observation. It had actually been observed back in the 40s. But we know that those long loops of Henle, have I confused anybody with loops of Henle yet? Okay. These long loops of Henle are very important in terms of conserving fluid. And so in other words, they're able to strongly reabsorb lots of stuff. Okay? So the idea was, well, I mean, the obvious way to control the amount of fluid that we lose would be to change the blood flow from one type of nephron to the other. So if we wanted to conserve fluid, we'd move blood flow to the long nephrons. That never really worked out, and so it's not in textbooks. I think that for you trying to get through exams, you just need to be aware that it's more of a histological thing than anything else. From a physiological standpoint, we don't have a lot to say about the difference between long and short nephrons, other than the fact that the long nephrons are clearly helping us to reabsorb stuff.